Action potentials are the really fast electrical changes that happen across the membrane of certain cells, and often propagates from one cell to an adjacent cell, and cells in the heart communicate this way. Now, that signal's gotta start somewhere, so some of these cells, called pacemaker cells, have the responsibility of setting the rhythm and pace of the heartbeat. So they've got this really important job, but they're a relatively tiny group, and make up only about 1% of the heart cells. But they're able to continually generate new action potentials that get conducted to the rest of the heart, or the other 99%. And so these are what tell the heart to pump. Now, pacemaker cells can also listen to action potentials from other cells, which usually come from neighboring pacemaker cells. But if those signals don't come, then a pacemaker cell will simply launch its own, and that action potential will then spread around. This property of launching their own signals is called automaticity, and it's pretty easy to remember since it's got automatic right in it. So let's start out by mapping these pacemaker cells. The first clump of pacemaker cells is tucked up here in the corner of the right atrium, and it's called the sinoatrial node, which is sometimes just called the SA node. We've also got pacemaker cells in the internodal tracts between the nodes, as well as in the atrioventricular or AV node, the bundle of His, and the Purkinje fibers. And together this is called our electrical conduction system. And all around these pacemaker cells are heart muscle cells, or cardiomyocytes, and they pick up the action potentials too, but that happens just a tiny bit more slowly. So we can think of these bands of pacemaker cells as highways that carry the action potential to its destination super fast. And then these muscle cells are like little side roads where it's a little slower. This is important because we want all of the myocytes to pick up that action potential and contract at about the same time. We can call this whole system a functional syncytium, which means that the mechanical, chemical, and electrical connections between these cells allow them to act as one unit in some ways. And it's the pacemaker cells that can make all of this happen. Okay, so now let's take a closer look at the chemistry that gets the action potential moving. Action potentials are initiated by depolarization, which is the opposite of polarization. Polarization is when there's a higher negative charge inside the cell relative to outside the cell. And that difference in charge is called the membrane potential. So if the membrane potential is negative, the inside of the cell is more negative than the outside. If it's positive, the inside is more positive than the outside. And if it's 0 millivolts, then the inside and outside have the same charge. There's 0 millivolts of difference. Alright, so the key here is understanding how the membrane potential changes. And it all comes down to the movement of ions. Specifically, two factors: which ion wants to move across the membrane and how permeable the membrane is to that ion. So depolarization is when ions move across the membrane and the membrane potential becomes less negative, or even slightly positive. You can kind of think of it like you have this one pessimistic negative cell that throws his hands up in a moment of positivity and joy. When one cell depolarizes enough, it can cause some ions to flow into neighboring cells, and trigger them to depolarize as well. If one cell after another depolarizes, then there's a depolarization wave, which you can imagine looks a little like a wave moving through a crowd at a football stadium. And each one of these depolarization waves causes heart muscle contraction. So the rate at which depolarization waves ripple through the heart actually sets the heart rate. This means that if depolarization waves are going through about once per second, then your heart is beating once per second, or 60 times a minute. Now let's focus on a single pacemaker cell going through a single action potential. The action potential of both pacemaker cells and myocytes are broken into 5 phases, often shown on a graph of membrane potential versus time. And we're actually going to start with phase 4. Phase 4 is the pacemaker potential phase, and it starts when the pacemaker cell is just sort of hanging out with an overall charge or membrane potential of negative 65 millivolts. Pacemaker cells have ion channels called hyperpolarization activated cyclic nucleotide gated channels, or just HCN channels, on their surface. That's a lot to take in, but basically these HCN channels are like gates that open when the membrane potential gets really negative, like negative 65 millivolts. And they specifically let in just positively charged sodium ions. Now, an electric current is a flow of electric charge. So when these sodium ions rush into the cell, then it's a type of current. And scientists have given it the name funny current, which is a super weird name. Anyways, as those sodium ions flow through the HCN channels, in other words, as the cell becomes more permeable to sodium, the membrane potential starts to depolarize slowly, or drift upwards all the way to about negative 50 millivolts. Now, after phase 4 is phase 0, and this phase is known as the depolarization phase, even though the cell was slowly depolarizing in phase 4. Once the cell's membrane potential reaches about negative 50 millivolts, voltage-gated calcium channels start to open up, which allows calcium to flow into the cell. With sodium and calcium flowing into the cell, the membrane potential rises all the way up past 0 millivolts and into positive territory, peaking out at about plus 10 millivolts. This happens super fast, lasting only about 0.5 milliseconds. Those calcium channels stay open until it hits about the plus 10 millivolt mark, at which point they start to close. Once the cells hit plus 10 millivolts, we're in phase 3, or the repolarization phase. You'll notice that we skipped 1 and 2. Well, it's because pacemaker cells don't have a phase 1 or 2. They just go straight from depolarizing to repolarizing again. At this point, the potassium channels open up and calcium channels close up. So the only ion channels that stay open are the potassium channels, which allow potassium to leave the cell, and the HCN channels, which allow sodium to enter the cell. Since there are so many potassium ion channels relative to HCN channels, there's a net outward positive current, meaning that positively charged ions are leaving the cell faster than they're coming in. So the membrane potential goes down again, all the way back down to negative 65 millivolts, which means that one full heartbeat has taken place. And then this whole process starts over with phase 4 again. Alright, as a quick recap, pacemaker cells generate action potentials automatically. Each action potential spreads through the heart muscle cells in a process called a depolarization wave. And each depolarization wave leads to a single heartbeat. For pacemaker cells, there are 3 phases. Phase 4, which is the slow depolarization phase. Phase 0, which is the rapid depolarization phase. And phase 3, which is repolarization.